All right, so it's time to go ahead and get started. So just to give you a heads up, today's lecture is going to be long. I know it's going to be over an hour, maybe like 90 minutes, something like that. So today's class is mostly the lecture, and then I have an activity on the lecture. I mean, you'll probably have some time at the end for lab, but Tuesday of next week, just about the whole class is going to be lab. Okay, because the beginning of Tuesday's class next week, I'll give you like an overview of lab 4, and then after that, it's basically work on lab 4.
For after this class, do we have enough knowledge to think about that for it?
You can do you can do some of it, yeah, just like previous weeks. But lab 4 tends to be the longest. In fact, I'm going to give you more time. Right now, lab 4 is scheduled for Wednesday of next week, like the other ones have been. But I'm going to change that. I'm going to make it later. And on Tuesday, I'll tell you what the new due date is.
Is this lab 4?
Yeah, that's the diagram for lab 4. There's a couple of things at the very end that I'll talk about. I mean, lab 4 doesn't really have a lot of, well, I should say lab 4 doesn't have a lot of additional code per se, but the reason why lab 4 usually takes people longer is because it involves signed binary numbers and also addition of signed binary numbers and subtraction by addition of signed binary numbers. And for some people, that takes a little bit to kind of get used to because it kind of looks strange at first. Okay, and that's what we're going to talk about in the lecture today. The lecture and the activity is all about signed binary numbers and how to do signed binary addition and how to do signed binary addition, subtraction by addition. Okay. So, I'll go until about the top of the hour, and then we will take a 5-minute break because, like I said, I know today's lecture is going to be longer than, the previous ones have been. Okay, so before we start into signed binary numbers, I just want to quickly review unsigned binary numbers. And also, I just want to emphasize, because I think sometimes this is the hurdle that some people have to clear in order to, understand signed binary numbers, and that's the zeros and ones, right? These bits, remember, in of themselves, they're just voltage levels, right? They're either 0 volts or plus volts on some piece of wire or printed circuit board trace. It's the designer that gives the meaning to the zeros and ones. So if we have a circuit and the binary data is unsigned, well, it's the designer that decided that. And if the designer decides to interpret the zeros and ones as signed binary numbers, well, the designer just decides that. There's not like these special bits laying around where some are signed and some are unsigned, right? So just always keep in mind that the zeros and ones in of themselves are just voltage levels, right? It's the design, the circuit that gives the zeros and ones their meaning, right? Because zeros and ones can represent anything. They can represent numbers, color, sound, whatever the designer wishes. Okay. All right. So just as a quick little review here, if I have these bits and it's a binary number like we've been doing, what is the value of this in base 10? Okay, well, remember, with an unsigned binary number, every bit has numerical value, right? And remember, we start here with the ones, right? The 2 to the 0. Right, this is the 2, the 4, the 8, the 16, the 32, the 64, right? So then we would just add them up, and what'd you say it was? 53. So I think that's right? Because
48 plus 5.
Yeah, 53. Okay. Everybody agree? All right. And then how about this unsigned number over here? What would the value of that be in base 10? Notice it's the same bits, except this is now 100. So
117. Yeah.
So we have a 1 and a 4 in a 16 and a 32 like we did before, right? But then we're adding 64 to it, right? So what would that be?
1/7.
1/7. Okay. Okay, so everybody can do this now, right? But you've done this a number of times. But the key point and the reason why I'm showing it now is because when you have unsigned binary numbers, every bit has numerical values. See, when you have signed binary numbers, the most significant bit, it doesn't have numerical value. The most significant bit tells you whether the number is positive or negative. Okay, so if you have a signed binary number and your most significant bit is a 0, well, that means you have a positive number. If the most significant bit is a 1, well, then you have a negative number. Okay, so what do we mean by most significant bit? We've talked about this before, the MSB, the most significant bit. Like in these examples here, where's the most significant bit? All the way to the left. Right, all the way to the left, right? This is the most significant bit here. Furthest to the left. And since we're talking about most significant bit, how about the other extreme, least significant bit? Where's that? Right, all the way over here. Okay. So when you have a signed binary number, the most significant bit no longer has numerical value. It just tells you whether it's positive or negative. Okay? All right. Well, next thing is there are 3 types of signed binary numbers. Okay, there's a signed binary number format, SM, that stands for signed magnitude. I don't really care if you remember what the acronyms stand for. Just know that there's 3 different ones. SM, signed magnitude. DRC stands for diminished radix complement. And RC just stands for radix complement. Now, DRC, this is also known as one's complement. Maybe in a math class, you heard of one's complement. In RC, a radix complement, that's also known as two's complement. Okay, so just 2 different words for the same thing. Now, the reason why I have RC, two's complement, underlined is because for this class and also for CP 233 and in most practical digital circuits or systems that use binary addition or binary subtraction by addition, they use two's complement. So the most common of these 3 by far, and I'll explain the reason why in a little bit, is two's complement. So that's the one we're going to focus on. I mean, I'm going to talk about these other 2 a little bit just so you know what they are, but the one you really need to know is two's complement. Okay? All right, so first thing is that for all of these 3 forms, okay, so for signed magnitude, one's complement, two's complement, the way you find the magnitude of a positive number is the same for all 3 formats. Okay, so for all 3 of these, finding the magnitude of a positive number is the same. Okay, so let's say we have this same string of bits here that we just figured out the value for when it's unsigned. Well, if we find the value of that same string of bits in signed magnitude, okay, so S down here for signed magnitude. Well, other than the fact that this most significant bit doesn't have numerical value but tells me it's positive, the way I find the magnitude is the same as when we do unsigned. Okay, so if this is a signed magnitude binary number. This 0 here, the most significant bit, that's the sign bit. So that tells me it's positive, and now I get the magnitude the same way I would with an unsigned, right? So this would be a plus 53. And that's true also if it's 1's complement. And it's also the same if it's 2's complement, right? For all of these, the magnitude would be the same. So you see there's absolutely no difference how you figure out the magnitude of a positive non-binary number, no matter what format. It's just the only difference is this most significant bit is the sign bit. Okay? Where the difference between the formats lies is when you find the magnitude of a negative number. Okay? Because depending on which one of these formats you're using, the magnitude of a negative sign binary number is going to be different. Okay, so that's the difference between the formats. So if I have this string of bits, and it's sign magnitude. Okay, well, this most significant bit's the sign bit, so that tells me it's negative. And to find the magnitude of a sign magnitude binary number, well, you do it the same way as an unsigned or a positive. This would still be minus, or this would still be 53. But because this is the sign bit, it's a negative 53. Okay? All right, now, if this is a 1's complement, okay, DRC 1's complement, same thing. Well, the sign bit still tells me it's negative. But now to get the magnitude of a 1's complement sign binary number that's negative, you flip the bits. And now you apply, this is the 1's column, this is the 2's column, 4 is the 8's, and so on. So you see, this would be a negative 10 in base 10. Right? And then if it's a 2's complement, okay, RC is the same thing as a 2's complement. Well, again, the most significant bit being a 1 tells you it's negative. And now to get the magnitude of a 2's complement negative binary number, you flip the bits and you add 1. You see, this would be negative 11 in 2's complement. Okay, so the key points here, when you have a signed binary number, the most significant bit no longer has numerical value. It either tells you it's positive or negative. If you have a positive signed binary number, the way you figure out the magnitude for all 3 formats is the same. And how you figure out the magnitude is the same as an unsigned. Okay, if it's a signed magnitude and it's negative, the way you find the magnitude is the same as an unsigned or a positive signed binary number. But what's different is when you get to the 1's complement and the 2's complement, right? As far as finding the magnitude, because if it's 1's complement, you flip the bits. That gives you the magnitude. 2's complement, you flip the bits and add 1, and that gives you the magnitude.
So you always flip them?
For DRC, you always flip them to get the magnitude if it's negative. Yeah, you don't do, remember, if it's positive, you just figure out the magnitude like an unsigned, right? Except the most significant bit doesn't have numerical value, right? The sign bit. Okay, so where the difference lies between the formats is how you find the negative magnitude. And again, of the 3, the one that's the most important is 2's complement. So when we have a 2's complement number that's negative, to find the magnitude, you flip the bits and add 1. Okay? All right, now we're gonna be doing a whole lot with this, so you're gonna get a lot of practice with it, but that, this is like the basics, okay? Now, if you look at the handout, I put a handout on each table. I think there's just one of these, yeah. There's just one of these at each table, so if you can kind of share and kind of look at this. And what I did on this handout is I showed the 4-bit signed binary numbers that you would get with sign magnitude, 1's complement, and 2's complement. Okay, so if you just take a look at those 3 formats, can you notice something kind of peculiar with sign magnitude and 1's complement?
-0.
Yeah, doesn't that kind of stand out? That those 2 formats, they have a -0 and a +0. What is -0, right? Because we think of 0 as being positive. Now look at the 2's complement. Do you see a -0 with the 2's complement? No, but what do you see? What value do you see with the 2's complement that you don't see with the other 2?
-8.
-8, exactly. So you see, that's a main reason why 2's complement is the most popular of all the formats, because 2's complement doesn't have 2 values but 0, right? A +0 and a -0. And plus you pick up an added value, right? You pick up -8, which you can't represent with 4 bits in the other 2 formats. You see, no matter how many bits that you have for your signed binary number, you're always going to have 1 extra value with 2's complement because you don't have a value to -0 like you do with the other 2 formats. Okay, so that's why 2's complement is the most popular one. Maybe there's applications out there where you do want 2 values of 0, where 1's considered positive, 1's considered negative. I don't know. If there are, then the other 2 formats would be, maybe useful. Okay. Got any questions on this handout? I would take a picture of the handout. I mean, I just put one on each table just because I was just going to reference it like I just did. But you may want to take a picture of it and use it as a reference yourself. Okay, so the next thing. Oh, the other thing I want to mention about this handout is that you're going to see that the term 2's complement has 2 different meanings. It has a meaning as a noun, and its meaning as a noun is what you see here, just this listing of numbers. But 2's complement also has another meaning as a verb. Okay, and we're going to get to that other meaning later. Okay. All right, so we did that. All right, now we want to talk about the range for both unsigned and signed. And I should probably move the camera at this point. Let's move this. Okay, so range. For unsigned and also 2's complement. So we'll start with the range for unsigned. Yeah. So if I have 3 bits, if I have 3 bits, so 3, 0s and 1s, right? What's the range of numbers I can represent if I only have 3 bits, if it's unsigned? Okay, we'll get to the general in a minute. But yeah, 0 to 7 just specifically, right? Because I can have all 0s or all 1s. Right, all 0s, all 1s, so 0 to 7. Okay, how about 4 bits? 0 to 15, right? You can fill in the bits here. 0 to 50. How about 5 bits? 0 to 31. So we can come up with a general expression for this range, right? Based on the number of bits. Obviously, the least of the range is going to be 0, right? Because no matter how many bits you have, they can all be 0. Right? So you see a general expression. It would be 0 how could I generalize this large number here based on the number of bits? Because 3 bits, I get 7, 4 bits, I get 15. Can you think of a general expression I could write?
2 to the n bits.
Say 2 to the n, would that be all that I would need? Minus 1. Right, because 3 bits, 2 to the 3, 8 minus 1, 7, 4 bits, 2 to the 4, 16 minus 1, 15, right? So see, that's our general expression for unsigned. Okay. All right, so now let's look at the range for 2's complement. Okay, remember RC, radix complement, and 2's complement, same thing. So sometimes you'll see me write it as 2's complement, sometimes you'll see it RC, same thing. Okay, so if we had 3 bits. Actually, let's start with 4 bits. Because 4 bits is on your handout. So on the handout, 4 bits, what's the range for 2's complement?
Maybe 7.
-8 to +7. Okay, you look at that handout, see how -8 is the most negative and +7 is the most positive. What do you think if we had 5 bits? What do you think the range would be? Yep, it's going to be -16 to +50. How about 3 bits? What do you think it's going to be?
-4.
Yep, -4 is great. Let's go 6 bits. Yeah, -32 + 31. So you can kind of see that, you know, it's with the unsigned 3 bits 0 to 7, 3 bits signed. See, it's almost like you're centering this range around 0 in a way. You think of it that way. But how about a general expression?
Two,
I'll let,
whatever.
wait a minute, let me write down general expression first. But okay, so how would we write the most negative? I heard someone started 2 to.
2 to the n minus 1, for the negative side, and then for the positive side, it'd be 2 to the n minus 1, then -1.
Negative.
Yeah, I need a negative. Yeah, so -2, that's an n, sorry. Right, again, n here stands for number. Right, so you can just test it by plugging it in, right? Because when we have 3, this would be 2 to the n, 3 minus 1, so 2 to the 2 with a minus, so -4. A 2 here, or a 3 here, excuse me, would give us 2 to the 2, 4 minus 1 with this 3. So everybody agree that we got this general expression correct? Okay. All right. Yeah, you're gonna see knowing these general expressions could be handy. Now, again, in CP233, you have data that's 32 bits, right? So the range for that microprocessor, you would just plug in a 32 for n, and it's 2 really big numbers. Okay, so any questions up to this point? Okay, this is all sort of preliminary, basic kind of stuff. Now we're going to get into the nitty gritty of addition of signed binary and subtraction or addition by subtraction of signed binary. Okay, so the first thing is that there are some validity rules. Okay, there are some rules to make sure that the result that you get from any signed binary addition makes sense, you know, that's valid. Okay, and these are the rules. When you add a positive to a negative, it's always valid. Right, because if you just think, if you take one of these ranges and you take a positive number within that range and you take a negative number within that range and you add them together, you have to be within that range, right? You could never be like outside. See, when you're outside the range, that's when it becomes invalid. Right, so it kind of makes sense. If you just think like a number line, right, with a positive and a negative limit. Right, if you had two numbers within that range, it's always going to be within the range, so it's always valid. Okay, if you add a positive and a positive, well, only valid if the result is positive. Right? And I mean, that just makes common sense, right? If you add two things that are positive, you can't get a negative, right? You can't add +3 and +2 and get -3 or something. Okay, so, you know, I don't think that one's too hard to remember, right? So what do you think about negative plus a negative? Has to be negative, yeah. So, negative plus a negative, only valid all right, so those are the validity rules of binary addition. Okay, so anytime you do a binary addition, you got to make sure or check it against this. Okay, to see if your result is valid.
That because like when carry through the goal, but the last bit.
Yeah, we're gonna see that in the example, but you're exactly right. Okay, so you ready for some examples now?
Yes.
Okay, okay, good. All right, so these are all two's complement. I forgot to put that up here. This is all, two's complement. So RC over here also. So like I said, that's the important one, is two's complement for what we're doing in here, what you're going to do in CP 233. And I would imagine anything you do in industry that involves signed binary numbers, you would use two's complement. Okay, so here we have our first example. Now, when we add signed binary numbers manually, we do it the same way as when we're adding unsigned binary numbers like we've done previously. The only difference is now this furthest to the left bit, which is the most significant bit, that's a signed bit now. Okay, but how I add the ones and zeros, it's the same rules as before. So, 1 + 1, 0, carry the 1. 1 + 1 + 1, 1, carry the 1. And then there would be a 1 here, and then this would go. Did I do that right? 1, 1. If I make a mistake, let me know. Right? So we added these two signed binary numbers manually, and this is our result. So based on our validity rules, is this result valid?
Yes.
Why is it valid?
It's always valid.
Right, it's always valid. We're adding a positive to a negative, so this is always valid. Now, what we could do next, I mean, this isn't absolutely necessary to do, but since we're first learning this, what we could do just to verify that indeed it's valid, and also get some practice on how to convert two's complement signed binary numbers into base 10, we could just convert all this to base 10 to make sure it makes sense in base 10. So what is this in base 10? Okay, it's positive. Right, and when it's positive, remember, you find the magnitude the same way you would an unsigned. So this is +3 in base 10. Okay, what's this in base 10?
5.
-5.
Yeah, how'd you get it?
Put all the bits and then add 1.
Yeah, so remember, the sign bit tells us it's negative, and now to get the magnitude, we just take the bits. Right, we flip them and add 1. So you see, when I flip these bits and then add 1, I get 5. So it's a -5. Okay. What's this in base 10? Yeah, it better be -2, right? Because +3 plus or -5 is -2. But again, if you flip the bits. Right, I flip the bits, 0, 0, 0, 1, and I add 1, 0, 0, 1, 0, that's 2. Okay, everybody see that? All right, let's do the next one. Okay, we got 1 plus 1. So 0, carry the 1, then 1, then 1, and 0. Remember again, this is the sign bit. So is this valid?
Yes.
Why is it valid?
Still positive.
Yeah, you're adding 2 positives and you're getting a positive result. Right? So this is valid. And can you see if we convert it to base 10? Right? This is 1 plus 1. This is plus 5. This is plus 6. Right? Okay. All right, let's do the next one. 0 plus 0, 0. 0 plus 0, 0. Let's see, 0 plus 1 is 1. 1 plus 0 is 1. Now again, this is the sign bit here. So is this valid?
Oh,
Yeah, always valid, right? Because it's a negative plus a positive, so always valid. Let's convert it to base 10 here, since there's some negative numbers here, just to get more practice with getting the magnitude of a negative 2's complement number. So what is this in base 10?
8. Negative.
Negative 8, right? Because see the sign bit being a 1 tells me it's negative. And now again, to get the magnitude, you flip, add 1. Right, so when I flip this, I get 7, and then I add 1, I get 8. So this is minus 8. And then what's this?
4.
Positive 4. Does this result agree? Right, because if I flip these bits and add 1, right, negative 4. Okay, let's keep going. Let's do this one. 1 plus 1, 0, carry the 1. These 3 ones give me 1, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. Not valid. Yeah, why is it an uh-oh?
Last time I checked, it had 2 positive.
Okay, yeah, see, we're adding 2 positives, we got a negative.
Should we check on?
So not valid. So let's convert this to base 10. What is this in base 10? 3 plus 3. What is this in base 10?
7.
Plus 7. Okay, so the reason I chose this example is because this is one of the common errors people make. And that's this, is, you know, they'll do all the manual adding the bits like we just did. And then they'll think about base 10, right? And they'll say, oh, you know, this is 3 base 10, this is 7 base 10. Oh, 1, 0, 1, 0, that's 10. So it's valid. But what is the mistake that person's making if they think,
Oh, that's a sign. They didn't know about the sign.
yeah, it's the sign bit. See, this doesn't have numerical value. This is the sign bit. See, you got to always remember the sign bit does not have numerical value. Okay. In fact, that's another way to think of not valid. Not valid is when you get a value that's outside the range for that number of bits. Okay. All right, let's do this one up here. All right, so 1 plus 1, 0, carry the 1. 1 plus 1 plus 0. 0, carry the 1, and 3 ones. 1, carry the 1, and 3 ones. So first of all, is this valid?
No.
I see a hand.
So the job that they and you get large. Large.
I'm not familiar with Java, but it sounds like
It's just an integer overflow. Or like if you go too high or. it'll-
Okay, well, that,
Yeah,
yeah, that's also how you can think of this, is when it's invalid, you're getting either an overflow or an underflow. So, yeah. Yeah. Okay, but, okay, remember, this is the sign bit. So first of all, is it valid?
Double negative.
Just looking at the sign bits, is this valid?
Yes.
Yeah, it's valid because I'm adding two negatives and I'm getting a negative result. Now, there's this one to the left of the sign bit. What do you think we do with that one that's to the left of the sign bit? You just ignore it. Right? It doesn't have any meaning. Something left of the sign bit is just baggage.
Innocent.
You just ignore it. It doesn't have no meaning. This is the result right here. The result is the sign bit and anything to the right of the sign bit. If you got something to the left of the sign bit, it's just baggage, like I said. Just ignore it. Okay, so we can convert these and again verify in base 10 that this is correct. So what would this be in base 10? -1, right? Again, sign bit tells us it's negative, flip all the bits, add 1, you would get 1. Okay, how about this? -3. And is this -4?
Yep.
Yeah. Right. Sign bits 1 minus, flip the bits, add 1, get 4. Okay. I mean, it kind of looks strange at first, but then, starts to, make sense after you look at it for a while. All right, let's do the last one here before we get to subtraction by addition. Actually, maybe the lecture won't be as long as I thought it was today. I thought it was going to be like 90 minutes, but it will be shorter. Let's see. 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 1 is 0. Carry the 1.
invalid,
Anti-valid. Yeah, why is it not valid?
because it's got a positive number. I don't know.
Yeah, we're adding two negatives and we're getting a positive result. So this is not valid. Again, you would just ignore any bit to the left, any one. Because that's the only time you really even concerned with it, but you ignore it. Right? If it's any bit to the left of the sign bit just gets ignored.
Is that an X or is that a Y?
Well, I'm Xing out the one so it looks like an asterisk. But yeah, or we can just erase it. However you want to do it, you can scribble it out, whatever, but just don't consider anything left of the sign bit in the result because it doesn't have any meaning. Okay, so any questions on sign binary addition? Half of the activity is just doing more examples like this. Okay, so if you understood these examples, when you do the activity, I wouldn't think you'd have, much difficulty. Okay, so are you ready for sign binary addition? Oh, actually, I put that backwards. Dude, I tell you, it was early in the morning. Sorry, this is subtraction by addition, not addition by subtraction. Sorry about that. I tell you, senility is not far away. Sign binary subtraction by addition. Okay, so you all know that A minus B is the same as if I take A and add it to negatives. Learned that way back in, I don't know, probably 4th grade or something, or even earlier. So recall back when we first talked about binary addition, right? And remember there was those rules, like 0 plus 0, 0, 0 plus 1, 1, and so on, right? That we talked about. And, we took those rules and we put in a truth table and we got a half adder. And then, we talked about how you would need a full adder because you could have the case of 1 plus 1 plus 1. Well, there are also rules of binary subtraction. you know, I would have to Google them, because I think the last time I saw them was when I took a class like this. Because you never use them. I mean, they exist, but you never use them. And can you think of a reason why? Because, I mean, we could take those subtraction rules and put those into a truth table and come up with a circuit for doing straight binary subtraction. But why do you suppose we wouldn't necessarily want to do that? Because if we could do subtraction by addition, what would be the advantage? Yeah, exactly. Right? That if I can do subtraction by addition, I can use the same hardware that does addition. Right? But if I did straight subtraction, I'd have these different rules, different truth table, different logic circuit. Like I'd have a whole nother new piece of hardware. But if you can use the same hardware to do different things, that's more efficient, right? Less gates. Right? So that's why, even though the binary subtraction rules exist, and I mean, if you're interested, you can Google them, and I'm sure you can find them. I've never used them, and like I said, last time I saw them was like 40 years ago. Okay, so this is where, see, this is where the other meaning, oh, I actually forgot to put this, I'll have to come back to this. This is where the other meaning of two's complement comes in, okay? Again, two's complement, the noun, that's looking at this column, right? Saying that, you know, these bits equal this particular value. That's two's complement as a noun. But then there's also two's complement as a verb. Like if you take the two's complement of any signed binary number, whether it's negative or positive, it's going to negate it. Okay, so see, if I'm going to do this subtraction here, what I would do is I would first write A, just like you see here. But then instead of subtracting it from this, I would add it to the two's complement by taking the two's complement of this. Because when I take the two's complement of any binary number, signed binary number, whether it's positive or negative, it negates it. Okay, so what would 0, 0, 1, 1 be if I go ahead and I take the two's complement, meaning I flip the bits and I add 1. 1, 1, 0, 1. Right, everybody see that? Because I would flip these, get 1, 1, 0, 0, and then add 1. Just to prove that it negated this, what is this value in base 10? Plus 3. What is this value in base 10? That's not close. It's got a minus here, so it's negative. And then when you flip the bits and you add 1, you're gonna get 3, right? Because it'd be 0, 1, 0, and then add 1. So you see, it didn't negate it. Right? By taking the two's complement of this plus 3, it made it minus 3. Okay, so now if you go ahead and do the addition, right? Whoops. So 0, 1, 0, 1, and now we're going to add it to 1, 1, 0, 1. So 1, 1, 0, carry the 1, 1, 1 plus 1, 0, 1, carry the 1. So you're getting ahead of myself. 1 plus 1, 0, carry the 1, that's a 1. 1 plus 1, 0, carry the 1. Get a 1. Like that. Now remember, this is the sign bit here. So is this valid? Yep, always valid because I'm adding a positive to a negative. So it's always valid. So this is valid. But actually, it'll be right on the other side. Right in front of us. We'll put it right here, valid. And then again, we can convert to base 10 just to double check. So what is this in base 10? 5. Plus 5. What is this in base 10? Minus 3. Okay, right, because again, remember this 1 is to the left of the sign bit, right? This is the sign bit of the result. So again, you just ignore that 1. So plus 2. All right. All right, let's do this one. So same thing, we're gonna do subtraction by addition. So you keep A the same, but now you add the 2's complement of this. You take the 2's complement of this. So what's the 2's complement of this gonna be? Flip the bit, add 1.
0, 0.
0, 0,
1, 0.
Oh, 1, 0.
1, 0. Right? Flip the bits. 0, 0, 0. Yeah, I think it's always good to actually write it out because it's easy to make a mistake when you flip the bits and add 1. It's easy to be like a bit off or something. So I usually always double check by just writing it out. But again, just to show you that by taking the 2's complement, it negated it. If you look at 1, 1, 1, 1, 0, what is this in base 10? Flip the bits, add 1.
2.
-2, right? This is a -2 in base 10. And you see, after we flip it, it's a +2. Well, flip it and add 1. Keep the 2's complement. So you see whether you're taking the 2's complement of a positive or 2's complement of a negative, it always negates it. It negates whatever you take the. See, again, this is 2's complement as a verb. 2's complement as a noun is that listing that you see. All right, so now we would just add these. So 1, 0, 0, 1 plus 0, 0, 1, 0. So 1, 1, 0, 1. This is the sign bit. So is it valid?
Always.
Yep, always. Negative plus a positive, always valid. So this is valid. And I'll let you convert it to base 10 if you want to prove it in base 10. All right, let's do this last one here. Actually, I think, I was saying before we'd have to take a break, but I'm surprised we actually went pretty fast today. So unless somebody objects, once we're done with this one, it won't take me that long to explain what else I have here. So we'll probably finish like around 10 past or quarter past. Okay, but let's do this here. So 0, 1, 0, 0, and then we're going to add to that the negation of this. So we're going to take the 2's complement of this. So what are we going to get if we take the 2's complement of this?
0, 1, 1.
Okay, so 0, 1, 1, 1. Everybody agree with that? All right, and again, we can prove that it negated it. Okay, because what is this in base 10 here? You flip the bits and add 1. Minus what? Let's flip the bits.
-7.
0, 1, 1, 0, add the 1. -7. And you see, after we take the 2's complement, it becomes a +7. Okay, and now if we add these. Let's see, we're gonna get 1, 1, 0, carry the 1. Is it valid?
Oh,
No, why not?
no.
Yeah, you're adding 2 positives, you get a negative, not valid. Yeah, because see, if you go to base 10, here you're adding +4 to +7, which is +11, and +11 is outside the range of 3 bits. Right, you can only go up to +7 with 3 bits, right? You can't go up to, of course, I'm pointing at the wrong one. I should be pointing at this one. Yeah, with 4 bits, 2's complement sign, the most positive that you can represent is +7. So our result, 11, isn't in that range. So that would be like an overflow. Yeah, we're previously with the negative, it's the underflow. So. Okay, so are you confident that if you had to do more of these, you could? Because that's what the activity is. The activity, there's 13 problems. Now, if you look at the activity sheet, there's more than 13 problems on the, activity sheet, but I only want you to do the ones that are circled. So there's like 7 here and 6 here. Some are addition, some are subtraction. But again, you're doing subtraction by addition, so you would do exactly what we did for these problems for those. And then I have the answers posted there, so you can check how you did. Oh, the thing I forgot that I want to go back to, I'm sorry about this. I forgot about this here. I forgot about talking about adding with zeros, sign extension. So let me go to this real quick, and then I'll come back to lab 4. Let's see. I am going to erase something. We'll erase this. Oh, I gotta change the camera if I do that. Let's come over here. So I don't want to move the camera again. So we'll come over here and do it here. All right, so let's first talk about padding with zeros, this term padding with zeros. Okay, this is something that doesn't come up in this class really, unless you do a team project that involves something with this. But you'll definitely hear this in CP 233. And that's, let's say you have some unsigned. Okay, so this has to do with unsigned. You got an unsigned binary number. It could be anything. Like, let's say it's just 1, 0, 1, 1, let's say. And for some reason, and when you take CP 233, you'll learn some reasons why this would be necessary. But for some reason, I want to take this 4-bit unsigned binary number, and I want to make it 12 bits without changing the value. So how could I take this 4-bit binary number unsigned and make it 12 bits without changing its value?
Between the sign and the,
Now this is unsigned.
oh, it's on, so you got your,
Yeah, since this is unsigned, if I want to make it more bits and not change the value, just add zeros to the left of the most significant bit, right? Like if I want to make this 12 bits, I would just add 8 zeros. Right? Because now it's 12 bits and it's still the same number it was before. So that's called padding with zeros. Okay, if you have an unsigned binary number and you want to increase the bits, but you don't want to change the value, just put as many zeros you need to put to the left of the most significant bit, right? Does that make sense? All right, now let's talk about sign extension. So let's say I have, 2's complement number that's positive. Like something like this. Doesn't really matter what the number is, but it's positive, right? So, again, this most significant bit tells me it's positive. So now, if I want to take this positive 2's complement number that's 4 bits, and I want to make it 12 bits without changing its value, yeah, you would just do the same thing, right? You would just put zeros to the left of that sign bit that's 0, right? 4, 6, 8, right? Because it's still going to be the same value now, right? Because the sign bit over here is 0. And the way you figure out magnitude of a signed binary number is the same as an unsigned, right? But what if this 2's complement number is negative?
Yeah, 1, or yeah, 1.
Yeah, you see that now if I want to make this sign, negative 2's complement 12 bits without changing the value, I would have to add 1s to the left, right? Because if I added zeros, when I go to get the magnitude, I'd flip those zeros to 1s, and that would change its value. So you see, this is called sign extension, that when you have a signed binary number and you want to increase the number of bits it has without changing its value, you take the sign bit and you extend it as many bits as you want. So that's where the name comes from, sign extension. Okay, like I said, both of these, padding with zeros and sign extension, unless you pick a team project where you might have to do something like that, It won't really come up in this class. It doesn't come up, you know, in the normal scheme of things. But the reason why I like to talk about it is because you're gonna hear about it in CP 233. You do this a lot in that class. Okay? All right, so let me go back to, am I still in view? Yeah. Let me go back to lab 4. So as I said at the beginning of class, for those that came in a little late, you know, this class today is mainly all, you know, lecture and activity. You'll be able to do some of lab 4, but you won't be able to do all of it until I talk about the overall design on Tuesday. And that's what I'm gonna do at the beginning of the class Tuesday. And it probably will only take me about 20 or 30 minutes. So Tuesday's mostly gonna be lab. There's also an activity that I'm gonna talk about that's a little bit different than what we've been doing. But yeah, Tuesday's class is gonna be a lot of, you know, less of me talking and more of you doing. Okay? Now, what you can do, okay, what you can do before Tuesday for lab 4 is that you can modify the RCA, because there's a reason that we want to make a modification to the RCA that you already have. And I'll explain the reason, you know, at the beginning of Tuesday's class. But the modification that we want you to make is that we want you to modify your RCA so it has all full adders. So right now, you know, from lab 2, and also you used it in lab 3, your RCA has 3 full adders and a half adder. Right, that's what you have now. The modification we want you to make is take that RCA that you have from lab 3 and change this to a full adder. And again, I'll explain the reason why at the beginning of Tuesday's class.
That maybe add an extra input for the period or you said it.
Very good. Yeah, that's where I'm going with this. Right. Is that, remember, the half adder has an extra input compared to the full adder, right? Remember how the full adder just has 2 inputs, A and B, but your full adder has A, B, and carry in. So when you change this half adder to a full adder, you're going to have this carry in, and you want to connect this carry in to an input for the RCA that you're going to call carry in, right? Because see, your new RCA, it's going to have the 2 4-bit inputs for A and B, like, you know, you have in lab 2, but now you're going to have a 3rd input carry in. And you're still going to have your 4-bit sum, and you're still going to have your 1-bit carry out. Okay, but your modified RCA, it's going to have a 3rd input carry in that connects to the carry in of this new full adder that you replace the half adder with. Okay, now like I said, there's a good reason why we're having you do this, and I'll explain it at the beginning of Tuesday's class. Okay.
For this.
I'll explain it at Tuesday's class. Now, make sure that after you do this modification, make sure you simulate it again. Don't, you know, I think sometimes students think, oh, I'm just adding another input, you know, I'm just changing this, oh, the full adders worked before. But believe me, I've seen plenty of times where people have done this and they, you know, they did something not right. And after they add the carry in, it doesn't work the way it should. And when you simulate this new RCA, use the same test cases that you used for the previous RCA, but then add test cases that test that it's adding this carry in when it's a 1. Right? If you make this a 0, then the test cases are the same as, you know, what they were previously. But you got to make sure that when this is a 1, it's adding that 1 to the other 2 inputs. Okay. All right. So that's one thing you can do. Another thing you can do before Tuesday for lab 4 is that you can create the validity checker. If you look on, there should be a handout at every table that shows you the overall circuit diagram for lab 4. And one of the modules is a validity checker. And that validity checker, it has 3 inputs and it has 1 output valid. Now, if you look at that diagram, where are those three inputs of the validity checkers going to? The inputs? There's three inputs. The output of the validity checker is going to a mux.
Those are coming from Israel signals.
Okay, specifically what signal? See how it says A3, B3?
Coming out of the mux from B, coming out of the first RCA, and then the other one's just pulled straight from A.
Okay, but why is there the three? Like why A3? Why T1 3, which is the
Because we need to
third bit
check.
of the sum?
Need to check
Or
the
T3.
positive.
Ah, exactly. The third bit, that's the sign bit, right? So you see how this is taking the sign bit of A. See, this is sign bit of A. This is sign bit of B. And this is the sign bit of the result. Right? It's taking the most significant bit of the addition along with the significant bit, which is the sign bit of what you're adding, right? I mean, why would that make sense? Why should that make sense to you that a validity checker to make sure that this binary addition is valid or not, that we're looking at the sign bits?
We got all this.
Because that's what the rules depend on. Yeah, you just care about the sign of what you're adding and the sign of what the result is. Okay, and then you just got the one valid output, make it 1 when it's valid, make it 0 when it's not valid. Okay, and there's two approaches to how you can design this module. One approach is to use an if statement. Right, it's basically taking these rules and put it into an if statement. Okay, so you can do that. I suppose you could also use a case statement, because whatever you can do with an if, you can do with the case. But most people, for this particular case, we do an if. But I'm not saying you can't do it with the case. You could probably do it with the case. But there's another approach that you can do. The other approach that you could do is you can make a truth table, right, where you have your sign bits on one side of the truth table, right, your input side, and then you have your output valid on the other side. And how many rows would we have in this truth table? 8, right, because we got 3 bits here, right, the 3 sign bits, so you'd have 8 rows. You'd have to put all the combinations, right? And then you would just look and see, oh, a positive plus a positive result positive, valid. That's a 1. Right, wherever it's a valid, you put a 1, wherever it's not valid, you put a 0. You could take this truth table, put it into a K-map, then from that K-map, get an expression for valid, and you could just have this module be an assign statement, right? Just assign valid to the Boolean expression that you get for valid. So it would be similar, or it would be exactly the type of procedure that you did in the first 2 labs. Okay, so for this validity module, you have some choices. Most people either do an if statement or they do a Boolean expression, for this table using a K-map to get the reduced. Okay, but like I said, you could probably do a case too. But all right, so the last thing today, before you start the activity, is that this is, you can do this because if you don't have this done by Tuesday, there's things I still need to talk about on lab 4 on Tuesday before you can do the whole thing. Plus, because lab 4 usually takes people a little bit longer than the previous labs, I will give you more time. Lab 4, even though right now lab 4 is due, if you look on Canvas, the due date is Wednesday of next week. I'm going to change that. I'm going to delay it some. I'll tell you how much I'm going to delay it on Tuesday. I haven't decided how much yet, but I'm going to delay it. Did you have a question?
Yeah, I still don't get how we can't do this right now. If all we have to make is the validity check, and say, can we just
Well, it's just the reason I'm saying a person doesn't have enough is just because I haven't explained the whole thing yet. So even if you
if
were,
we can read this, or we just
well, you can always do more. Yeah, I mean, if you feel confident that you can do all that, by all means, yeah, I don't want to
Okay.
slow you down. But I'm just saying that I'm not, I'm not telling people to do the whole thing yet because I haven't explained it. And really, you gotta know how it works as a whole to know whether the simulation for the whole is gonna be correct. So, but yeah, by all means, if you ever want to do something more, no problem. In fact, I love it when students do more than what they're asked. Okay, but last thing here, and again, this is a can do, but this is a must do. And I guess that's another reason I didn't make this, definitely have to do this. I'm giving you something else that you have to do before Tuesday's class. Before Tuesday's class, I want you to watch the video that's on Canvas. Just show you where it's at so it can you.
Because we decide what all those ballots and the first one.
So there's a video on Canvas that Dr. Benson made. And this is one of the most important videos, not only for this class, but for CPD 233, because in this video, Dr. Benson shows you a technique that is super useful for troubleshooting when you start to get into more complex circuitry. See, this is getting pretty complex, right? Because, what is there? There's like a half a dozen modules. And when you build your microprocessor in CP233, you're going to have like a dozen modules. Okay. So hopefully this will come up. Yeah. So right here on Canvas, in the modules, if you go to lab resources, right under general troubleshooting steps is this Dr. Benson troubleshooting video. And what she shows in that video is that, when you run a simulation, what outputs appear on that simulation, like the simulations that you've been doing, right? And you go to look at it, like what outputs are being shown on that timing diagram? The top module, right? Like this last one for lab 3, it was showing seg and AN. Right now, it'll also show the inputs, but the key thing is it's showing the output of the overall module. It's not showing any signal that's within that high level. Well, in this video, Dr. Benson shows a technique where you can put any signal onto that timing diagram. You can look at any internal signal. And you see, that's really valuable for troubleshooting because when you start getting into these larger circuits, sometimes your lower level modules will all simulate correctly. And you'll look at the schematic, the elaborated design, and it will look like it's connected correctly. In fact, I had a student during my office hours yesterday. It was exactly that, the lower level module simulated correctly, but she was getting something funny on the timing diagram, but we looked at the schematic, elaborated design schematic, and it wasn't obvious that anything was incorrect there. So we basically used this technique and we were able to find the problem. It ended up being just a typo in the sim file, typo of some internal signal or something. I can't remember exactly what it was. But anyway, when problems get a little bit more complex, the technique that Dr. Benson shows, and it's basically you can take any internal signal and drag it over to the timing diagram, and then you just got to restart the simulation and you can run it for a specific amount of time, and you can get that waveform onto the timing diagram. Okay, so before Tuesday's class, watch that video so you know the technique, and I would actually practice it too. Because during Tuesday's class, the activity is going to be that you have to show me. And this is every student, this isn't each table. So this activity is each person. Each person needs to show me that they can do it. And, either use lab 2 or lab 3 to show me that you can take an internal signal, put it onto the timing diagram, and then you got to restart it and run it for a specific amount of time. And if you do that, you get checked off. Okay. You're probably not gonna have enough time to watch the video and do the demo during class. So that's why I say watch the video ahead of time and even practice it so you know what to do. And then you can show me right when you get to class after I'm done with the, the short lecture. Okay? All right, so I think that was it. So do you have any questions before you get started with your work today? All right, well, if questions come up, please ask. We got people not here today. This is not a good day to miss.